turned down 200 applicants. And on top of that, you had the fortune of seeing the lion dancer performance. Now I would like to introduce the second laureate, Dr. Alan Guth. Please watch the video that was shown during the prize ceremony.
I find to imagine that we can think thoughts about what we hypothesize the universe to have been like 10 to the minus 30 seconds after the instant of the Big Bang, and find predictions from those thoughts that can actually be verified, making the whole picture look true, as fantastic as the extrapolation seems. And this is what it's all about. The key idea that the three of us are being awarded the prize for is something called inflation. It's basically an answer to the question of what drove the Big Bang. What was the propelling force that drove the universe into this gigantic period of expansion that we're still experiencing? And it really has been an amazing feeling to contribute to the ability of mankind to understand the universe in terms of some mathematical equations.
So you're a superstar now.
I guess so, I guess so.
Thank you. Professor Guth's achievement is a discovery of the theory of cosmic inflation. Professor Kazuhiko Sato is also a researcher of inflationary theory, as you might know. But inflation theory was coined by Professor Guth. In Big Bang theory, it says that there was a start to the universe. A universe at the very start was expanding rapidly, and that is expansion. And how rapid was it? It was as small as a bacteria, and that universe in an instant became as large as a galaxy. You might feel that this is stupendous and inconceivable, and on the surface it might appear as though it's a crazy theory, but many Big Bang issues were resolved with inflation theory. As I listened to Dr. Guth, theoretical physicists, including myself, will go through a postdoc research phase once or twice after graduating, after obtaining PhD, and will become associate professor at a certain university. But as it turned out, I heard from Professor Booth that he was postdoctoral researcher 4 times, and I asked him whether he was anxious, and he said he was a little anxious, but after he published his inflation theory, he became a full professor at MIT without becoming assistant professor at all. And 2 years ago, at a Kavli Laureate lecture held in Japan, Japanese Kavli Laureate, Professor Sumio Iijima spoke, and I offered a commentary on theory on inflation. And at the time, the Minister of Research and Education for Norway was here, and I tried as hard as possible to explain it in a way that is understandable for politicians. Inflation is ensuring equal opportunity in the universe because it is the same anywhere in the universe, and that is resolved with the horizon issue. And after the equality is issued, there will be a start of diversity in the universe. And the minister enjoyed this and understood the importance of inflation. I hope that funding will increase for theoretical physics research. This is a fundamental issue. Where did we come from? How did the universe start? It may not have direct application, but this is a fundamental curiosity that human beings have. And as for Professor Guth, if I may complain only on one thing, when I visit MIT to give a lecture, Professor Guth kindly attends, but he always falls asleep during my lecture, and I'm worried that my speech was very boring. But at the end of the lecture, he wakes up and he asks the most astute question. So he is extraordinarily intelligent. Professor Guth, please welcome Professor Guth with a big round of applause.
Thank you very much, Hitoshi. I think you exaggerated a bit about the astuteness of that question, but outside of that, probably what you said was true. I want to say that this has been my first visit to Japan, and I have really enjoyed it. Everybody has just been wonderful to me, and I'd really like to thank my hosts. and say that my visit has been wonderful, and I'm sure that now that I've been to Japan, I will try to get back here often. I'd also like to comment that this is the first time I've given a lecture after recently having been bitten by the head of a lion, and that should make it very exceptional. And we'll see if that tradition is true. What I want to be talking about today is cosmic inflation, the subject for which I and Andrei Linde and Alexei Starobinsky were awarded the Kavli Prize. As was included in a little clip that you saw, inflation is basically an attempt to explain what was the bang of the Big Bang. What is it that drove the propulsion of the Big Bang itself? A subject which, surprisingly, the traditional Big Bang theory really says nothing about. I'll be dividing my talk into three pieces. The first piece will attempt to describe what inflation is and how it works. The second piece will discuss what evidence we have that our universe actually underwent this process called inflation. And the third will be this idea of a multiverse. It turns out that inflation does not in any way imply rigorously, but it does strongly suggest that our universe is not alone, but in fact we live perhaps in a multiverse composed of many universes. And I'll try to explain what the rationale is behind that. And by the way, happy Halloween. I want to begin at the beginning. So I'm going to start by saying a few words about the conventional Big Bang theory as it stood before inflation came along. And the conventional Big Bang theory is essentially the theory that the universe as we know it began some 13 to 15 billion years ago. And now, in fact, we have a very precise estimate for the age of the universe, 13.82 plus or minus 0.05 billion years. The initial state was a hot, dense, uniform soup of particles. And in the context of this conventional Big Bang theory, the assumption was that the matter filled space uniformly from the very beginning. And this uniform distribution of matter was rapidly expanding, again, from the very beginning. That was just the hypothesis about how everything started. This conventional version of the Big Bang theory describes how the early universe expanded and cooled. It describes how the light chemical elements formed. And it describes how structure formed from gravitational clumping. Initially, everything was almost completely smooth. The important aspect for the current talk, though, is what the conventional model did not describe. And in particular, it says nothing about what caused the expansion. Even though somehow this theory got to be called the Big Bang theory, it really said nothing about the bang. It was really just a theory of the aftermath of a bang. I like to say that it says nothing about what banged, why it banged, or what happened before it banged. It really is a bangless theory. In addition, the conventional version of inflation said nothing about where the matter came from. In the conventional version of the Big Bang, for every particle that exists in the universe today, there was at least a precursor particle that existed from the very beginning of the description. So it turns out that inflation does provide possible answers to these questions, which is what we'll now go on to talk about. Inflation, as I said, is essentially a theory of the bang of the Big Bang. That is, it's a possible answer to what propelled the gigantic expansion of the Big Bang theory. And before inflation was discussed, there really was no even attempt at an explanation of what caused the expansion of the Big Bang. It was just assumed. Inflation explains this expansion by means of gravitational repulsion, which is itself something that may sound a bit strange to many of you, depending on how much you have followed these recent developments. According to Newton, gravity is strictly attractive. However, starting with general relativity, the possibility of repulsive gravity was introduced. Now, I like to think of gravitational repulsion as a kind of a miracle of physics. And I'm going to be describing inflation as essentially being the consequence of two miracles of physics, the first of which is gravitational repulsion. Now, since scientists are not supposed to believe in miracles, I'm told, I'd like to define what I mean by a miracle of physics. The definition of a miracle of physics is it's a feature of the actual laws of physics as we understand them, which has two properties. A, it was never taught to me when I was a student. And B, it has consequences that are so far-reaching that it can really change our picture of how the universe works. And as I said, inflation essentially invokes two of these miracles of physics by my description. So the first is this idea of gravitational repulsion, which has existed since the advent of general relativity, which is now almost exactly 100 years old. So it's an important anniversary. Einstein actually took advantage of this possibility of gravitational repulsion very early on, about a year after he first proposed the theory of general relativity. He attempted to apply it to the universe as a whole and discovered, as is now sort of famous, that if one just had ordinary gravity, the static universe that he believed was the description could not remain static. It would collapse under the influence of ordinary gravity. This is usually now regarded as a natural consequence for Newtonian gravity as well, although Newton did not realize that. He, in fact, talked himself out of it. But the point is that gravity is attractive. So if you want to have a static universe, and Einstein was convinced at this time that the universe was static, you have to do something about the fact that gravity pulls everything together. So Einstein realized that there was a term he could add to his equations completely consistent with the basic theory of general relativity, which would produce a gravitational repulsion that would hold the universe up against this force of collapse. And that's what he called the cosmological constant and the cosmological term that the cosmological constant is part of. But it really is just a feature of general relativity. Modern particle physics looks at this cosmological term very differently. Einstein regarded it as just an extra term to add to his equations. From the modern point of view, we realize and take full notice of the fact that that term that Einstein added is exactly the term that he would have added if somebody told him that the vacuum had a non-zero energy density. Einstein did not look at it that way, but it is exactly the term that would be added if the vacuum, empty space, had a non-zero energy density. And that's how modern particle physicists look at it. We view this cosmological term as simply vacuum energy, and it does create gravitational repulsion. And furthermore, according to modern particle physics, at super high energy densities, I mean far beyond what we can actually reach in the laboratory, we expect there to exist a large number of states which create repulsive gravity in the same way as vacuum energy does. Actually, they incorporate essentially vacuum energy. So repulsive gravity is now part of our picture of how gravity works, of what gravity can do. So the sequence of events that this inflationary theory proposes is that at least a patch of this repulsive gravity material existed in the early universe. It does not have to fill the early universe. It's sufficient to have a very small patch. We don't know exactly what energy scale inflation happened at, which is another way of saying we don't know exactly when in the sequence of very early universe events inflation occurred. But a typical, a plausible theory is that inflation was associated with what are called grand unified theories, which would give us an estimate of the energy scale of inflation. And the numerical examples I'll give will be based on that assumption, the assumption that inflation was attached to grand unified theories. In that case, the initial patch needs to only be as large as 10 to the minus 28 centimeters. And I'm sure most of you know what that means, but for those of you who don't, 10 to the minus 28 means a 0, a decimal point, 27 zeros, and then finally a 1, that fraction of a centimeter. Now, since the patch is going to be fantastically enlarged by inflation, the initial density of these patches, or even the probability that they might exist at all, can be very low. As long as you find at least one of them, you can produce a universe from it, and that's all we need to do, is to produce a universe. Once such a patch exists, the gravitational repulsion, which the patch produces, becomes the driving force behind the Big Bang. The patch would be driven into exponential expansion with a doubling time of about 10 to the minus 38 seconds, an unbelievably short period of time. So every 10 to the minus 38 seconds, this little patch will double in size and then double again and then double again. And this process of successive doubling is incredibly efficient at making a large object from a very small object. And in particular, for the patch to expand to become large enough to ultimately become our universe, we need an overall expansion factor of 10 to the 28. But that requires only about 100 doublings. I defined 10 to the 28. It's a 1 followed by 28 zeros, in case you didn't know. But it requires only about 100 doublings to increase the size by a factor of 10 to the 28. So the 10 to the minus 28 centimeters becomes about 1 centimeter, about the size of a marble at the end of inflation. And this marble then continues to expand, no longer accelerating, no longer doubling every 10 to the minus 38 seconds, but it continues to coast in its expansion until the present day, when it's now as large as everything that we see. Inflation ends because this repulsive gravity material that's driving the expansion, driving the repulsive gravity, is unstable. So it decays very much like a radioactive substance decays. And when I use the word decay, I mean it converts into other forms of matter which do not create gravitational repulsion. When the decay takes place, it releases a huge amount of energy, and the energy of that decay becomes ordinary particles, which forms a hot, dense primordial soup of particles, which is exactly the starting point for the conventional Big Bang theory. So inflation sets up the initial conditions for the conventional Big Bang theory, essentially the same initial conditions with a few more details added, but essentially the same initial conditions which had been previously assumed in the context of the conventional Big Bang theory. Now, a very important feature here is that we're undergoing a fantastic amount of expansion, 10 to the 28 in linear dimensions. And that means if the volume goes like the cube of the linear dimensions, so that's 10 to the 84. So it's a fantastic amount of expansion. If the matter inside this region thinned out the way normal matter does, there would really be nothing left after you expanded by a factor of 10 to the 28, and you would never get a universe that way. So what's very strange here is that as the expansion takes place, and even though more and more mass and energy are appearing in this repulsive gravity material as the exponential expansion proceeds, the energy remains constant. It does not thin out. And nonetheless, this is consistent with the principle of energy conservation. Now, that sounds strange, and you might realize that we're about to invoke our next miracle. We need a miracle here. But it is a miracle of real physics. How could this happen? It happens because although energy is conserved, something which most of us think about energy turns out not to be true. Energies are not always positive. Energies can be negative. And in particular, the energy of a gravitational field is actually negative. And this is really true in Newtonian physics as well as in general relativity. It works either way. And what's happening during inflation is that more and more positive energy is appearing in the material that fills this inflating region, a fantastic amount of energy. But at the same time, a fantastically large negative amount of energy is appearing in the form of the gravitational field that also fills this exponentially expanding region. So the balance sheet goes something like this. There's a huge positive contribution of matter and radiation, which I show in the black using the standard economic colors of black for positive balances and red for negative balances. But there's a huge red negative contribution from gravity. So the total balance sheet for the universe is actually consistent with zero. The total energy of our universe, as far as we can tell, is zero. That is, we don't know for sure if these balance exactly, but it's consistent with coming out to exactly zero for the total energy of the universe. And inflation depends upon that, because inflation starts the universe with an incredibly small or even perhaps zero energy, and from it produces the entire universe that we see. Okay, that finishes the first part of my three-part talk. Remember, the first part is the description of what inflation is and how it's supposed to work. Now I want to move on to part two, which is I want to tell you about some of the evidence that this story of inflation that I just told you is not just a story, but is very likely the way our universe, in fact, came into existence. So I want to actually point to three pieces of important evidence here, or 3.5. So there'll be one at the end that will be maybe a piece of evidence, probably, maybe not yet. But there are three that are very solid. The first is the large-scale uniformity of the universe, which is something that we take for granted, but theoretically it's very hard to understand. And in the context of the conventional Big Bang theory in particular, it's very hard to understand why the universe is so uniform. Now, what do I mean by uniform? There's, of course, a lot of details in the universe that are not uniform. There are galaxies, clusters of galaxies, planets, cities, everything. But on the largest scales, the universe does appear to be homogeneous. That is, if you average over large patches of billions of light years, each patch looks the same as every other patch. And this uniformity is seen most clearly by looking at the cosmic background radiation, which is really the most distant thing that we can see when we look out into the universe. And this cosmic background radiation is known to be uniform in its intensity or in its temperature, as the astrophysicists talk about it, to an accuracy of 1 part in 100,000, which is really unbelievably uniform. And the question is, how did it get that way? Now, one possibility is you could just assume, since we don't really know how the universe started, and inflation doesn't really attempt to explain how the universe ultimately started either, you could just say somehow it started completely uniform, and we don't know why, but it just did. That's still a possible explanation. But if you want to try to have an explanation for the uniformity, to not simply assume it, then you face a fact that it's essentially impossible in the context of the conventional Big Bang theory to achieve this degree of uniformity in the amount of time available. And that's this magic number, 380,000 years. This cosmic background radiation was released when the universe was 380,000 years old. By released, what I mean is that prior to that time, the matter in the universe was so hot that it was a plasma. That means free electrons were ripped off of the atoms, and you had just nuclei and free electrons floating through space. It turns out that such a plasma is very opaque, very non-transparent to photons, to light. So the photons of the cosmic background radiation were there then, and they were moving at the speed of light at any given instant. But the photons were constantly scattering off of the free electrons, mainly. And because they kept scattering and changing directions, even though they were instantaneously moving at the speed of light, they really didn't get anywhere for the first 380,000 years. So for that period, you could think of the photons as just being tied to the matter. But then at 380,000 years, according to our calculations, the universe cooled enough so that the matter neutralized, became a neutral gas instead of a plasma, just like the air in this room is a neutral gas. And such a neutral gas is incredibly transparent to photons. So the photons that we now see in the cosmic background radiation have almost entirely been traveling on straight lines since 380,000 years after the beginning. And that means that it really gives us an image of what the universe looked like at 380,000 years, just as the light traveling from my face to your eyes gives you an image of what my face looks like. So the conclusion is that the universe was incredibly uniform at 380,000 years. That's the key point. So whatever mechanism you want to imagine smooth the universe out, it has to be able to do it by 380,000 years. So we know that things do tend to smooth themselves out. It's sometimes called the Zeroth Law of Thermodynamics. So the air in this room spreads out to fill the room. And if we closed all the doors and stopped breathing and things like that, it would approach a very uniform temperature as well. So one can ask, could that be what made the universe so uniform? Maybe it was just like a gas spreading out and coming to a uniform temperature. But it only takes a short calculation to conclude that that's not possible in the context of the conventional Big Bang theory, because you can compute how fast things would have to move to be able to do that by 380,000 years. And the answer is that to smooth the universe out by 380,000 years, it would require the transmission of energy and information at about 100 times the speed of light. And according to the laws of physics as we know them, nothing goes faster than light. So it's simply not possible in the conventional Big Bang theory to explain the uniformity that we observe. Inflation, however, gets around that in a very simple way. Inflation modifies the history of the universe by adding to it this period of extremely rapid exponential expansion. And that means that in an inflationary model, if I imagine the observed universe today and try to follow it backwards in time, when it goes through inflation, it becomes incredibly, incredibly tiny. That tiny size we talked about of 10 to the minus 28 centimeters at the start. When the universe is so tiny before inflation, there's plenty of time for it to become uniform by exactly the same kind of processes that makes the air in this room spread out and come to a uniform temperature. And then once the uniformity is established in this very tiny region, then inflation takes over and expands it to become large enough to include everything that we see. And that is the explanation of the uniformity in the context of inflation. And it means that inflation gives us a very simple explanation and really a prediction that the universe should look very homogeneous, exactly like it does. Next item that I want to talk about, the second of three, is called the Flatness Problem. And this is the question of whether we can explain why the mass density of the early universe was so close to what is called the critical value, which is defined to be the value which, according to general relativity, corresponds to a flat or Euclidean universe. According to general relativity, space in general can be curved, and only for a particular value of the mass density would the geometry of the universe be Euclidean. Cosmologists define a quantity called omega, the Greek letter capital omega, as the ratio of the actual mass density divided by this quantity called the critical mass density. I should maybe mention here that this critical mass density depends on the expansion rate. It's not a universal constant. But for any given expansion rate, there's exactly one mass density that would make the universe Euclidean. So when omega is equal to 1, that means that the universe is Euclidean. If omega is greater than 1, it's called a closed universe. And if omega is less than 1, it becomes an open universe. The problem, that is why it's difficult to explain why omega is close to 1, is that the evolution of the universe always pulls omega away from 1. No matter which side omega is on, it will always be pulled away from 1 as the universe evolves. So to be anywhere near 1 today, which we know it is, it has to have been extraordinarily close to 1 at early times. And to give a sample number, if we go back to 1 second after the beginning, we know that to be within the range that we see today, omega then has to have been equal to 1 to an accuracy of 15 decimal places. I often sometimes joke and say that this indicates that the most accurate number that we know in all of physics is the mass density of the universe at 1 second after the beginning, because it's really true. And the reason we know it so accurately is simply that the evolution of the universe has amplified for us any deviation that omega had from 1. And because of that large amount of amplification that the universe itself has provided, we know to extraordinary accuracy what omega was at any early time, 1 second here being used as an example. But the conventional Big Bang theory includes nothing to indicate how omega got to be so close to 1. In the conventional Big Bang theory, the initial value of omega could have been anything, and the theory would be equally logically consistent. It would just not lead to a universe that looks like the one we're living in. So omega could have been 2 or 10 to the minus 1 or whatever, and it would just lead to a very, very, very different universe. So how omega got to be 1 is a mystery in the conventional Big Bang theory. But inflation has a simple solution. It turns out that during inflation, because gravity is acting very differently, gravity is acting repulsively instead of attractively, during inflation, omega is driven towards 1 instead of being driven away from 1. And it's being driven incredibly rapidly towards 1. So with inflation, now the value of omega before inflation really could have been anything. And we would still get a universe that looks like ours, because the inflation would drive omega extraordinarily close to 1. Furthermore, it leads to a prediction, and it's a real prediction because when inflation was invented, nobody really knew much about the value of omega. We knew that to within about a factor of 10 or so, it was equal to 1, but that was all that was known when inflation was first invented. But this mechanism that drives omega towards 1 is so effective that the prediction is that omega should still be 1 today, as far as any reasonable measurement could tell. But that, for a while, was a problem. Until 1998, most astronomers were converging on the idea that omega was looking not like 1, but something like 0.2 to 0.3. Now, I might just say on a personal note here that this made it very uncomfortable for me to have dinner with astronomers pre-1998. They would have a tendency to sneer a little bit and tell me that, yeah, they think inflation really is a beautiful theory, but it's really only a theory which can't actually be right because it predicts omega is 1, and it's pretty much evidence that omega is not 1. Omega is 0.2 or 0.3. So I ate my dessert and got through the dinner, but it was never very comfortable. But things changed in 1998. And since 1998, omega has been converging on 1, and the latest value, latest experimental value for omega is that. We know, in other words, the error is the important thing here. This happens to be very, very close to 1, but we only know it to about 0.5%. So omega now has been measured to about 0.5% and agrees with 1 beautifully. So inflation now considers this a big success and not the problem that it was before 1998. And the difference, what changed in 1998, was the discovery that the universe is not slowing down under the influence of gravity, but instead, for the last 5 billion years or so, the universe has actually been accelerating in its expansion. And this, of course, is very much like inflation itself. It is, in fact, viewed as being an example of a repulsive gravity. And it says that the universe today must be filled with a repulsive gravity material much less intense than what I was talking about during inflation, but basically the same characteristics. And that stuff, the stuff that's driving the acceleration of the universe today, we call the dark energy. And we can calculate how much of it there must be, even though we don't know exactly what it is for sure. And when that gets added in, that's what gives this beautiful value of omega. So the discovery of the dark energy changed the situation completely in terms of the success of the inflationary prediction. OK, now I want to move on to my third and I think most impressive piece of evidence for inflation, which has to do with the small-scale non-uniformities that we see in the universe. On the larger scales, I told you it's incredibly uniform. And overall, it's incredibly uniform to an accuracy of 1 part in 100,000, which is incredible. But what's even more incredible is that now astronomers have gotten so good at devising measurements of the cosmic background radiation that they can measure non-uniformities that exist at the level of 1 part in 100,000. Tiny ripples on the top of an almost perfectly uniform background. And now they can measure these tiny ripples to extraordinary accuracy. And they can be compared with predictions from inflation. Inflation has a way of producing these ripples, and that method itself is somewhat extraordinary. Inflation in the context of classical physics, and by classical physics I mean all physics other than quantum physics, inflation in the context of classical physics would just smooth the universe out by the enormous stretching effect of this gigantic expansion. But quantum theory changes that because quantum theory is fundamentally a probabilistic theory, not a deterministic theory. So where the classical theory would predict a completely uniform mass density at the end of inflation, the quantum theory predicts that in some regions it will be a little bit higher than that average, just by random quantum fluctuations. And in other regions it will be a little bit lower than that average, again, just by random quantum uncertainties. And that produces this pattern of ripples, which is exactly what we are looking for to explain the ripples that are observed in the cosmic background radiation. Now, I should confess that we don't know enough about inflation to actually predict how high these ripples should be, the amplitude of the ripples. But what we can predict from our understanding of how quantum theory meshes with inflation, we can predict what's called the spectrum of the fluctuations. And by spectrum, I mean pretty much exactly the same thing you would mean if you talked about the spectrum of a sound wave. When you talk about the spectrum of a sound wave, you have in mind that any sound wave can be broken up into components that have definite wavelengths. And the spectrum is how much intensity of each wavelength you need. Same thing here. The pattern of ripples in the mass density after inflation, or as we see it today in the cosmic background radiation, can be broken up into components that each have a definite wavelength. And then you can talk about how the intensity varies with the wavelength. And this has now been measured to rather extraordinary precision. These are the kind of maps that these experiments give us. This is a map of the temperature of the cosmic background radiation at every direction in the sky. This oval is a mapping of the entire sky. And the blue and red spots indicate different temperatures. Now, it is almost completely uniform. These are false colors. The temperature variations are shown on the scale down here, and they're in microkelvin compared to the 2.7 Kelvin, which is the overall temperature. So this is just a part in about 100,000. But amplified. Now, from this picture alone, just looking at it, all you could really do is be impressed, I think. It's hard to know what to make out of it. But you can analyze this picture to figure out what the spectrum is. How does the intensity of the different wavelength components vary with the wavelength? And that leads to this marvelous graph, which comes from the Planck satellite. And this comes entirely from the Planck satellite. One often combines this data with other data from other experiments. The dots are the actual experimental points. Oh, I should maybe describe the axes first. The vertical axis is the magnitude of the temperature fluctuations. And the horizontal axis is the wavelength, where the wavelength is thought of as an angle, because what you're really just seeing is a pattern on the sky. You don't know what physical distance those angles correspond to necessarily, so you just plot it as a function of the angle. So on the bottom axis, we have the angles expressed in degrees. On the top axis, we have these things called multipoles, which if you know about them, that's how the experiment is actually done. But the multipoles really do just correspond to angles. So it's sufficient to understand the bottom axis. So this is the spectrum. It's a plot of the intensity of the ripples as a function of angular scale, as a function of the wavelength. And the little dots are the data. You can see error bars on some of them. Some of them have error bars too small to show. If you can't see an error bar, it means the error is smaller than what you can see. And the green line is the prediction of inflationary models. There are a few parameters that are being fit here. In principle, it's a 6-parameter fit. But actually, for 4 of those parameters, we pretty much know the values from other observations, and they agree. They fit well. So there are really 2 important variables here that are being fit. One is the overall height, which I mentioned. We don't know enough about inflation to actually predict the height of these ripples. And the other variable that's being fit here is something having to do with the absorption of radiation between the place where they're released and the present location. It's 1 parameter. But it's a fantastic fit. And I believe it provides very extraordinary evidence for inflation. And I think other people do too. As a sample comment, there was a report done by the American Physical Society. They created a study group to plan future cosmic microwave background experiments. And this 94-member group came up with this composite statement that current measurements of the cosmic microwave background and observations of large-scale distributions of dark matter and galaxies in the universe are in stunning agreement with the concept of inflation. So I think that's the community-wide conclusion of how to interpret this data. So big success for inflation as far as I'm concerned. I wanted to say a little bit about gravitational waves, because it was a topic widely discussed in the press over the last year and a half. In the end, we don't know much yet about what the story is concerning gravitational waves. Inflationary models predict that there should be gravitational waves in the early universe produced by the inflation itself in a manner that's similar to the way these density fluctuations that I just showed you are produced. But the intensity of the gravitational waves depends very much on the details of the inflationary model. Some produce very large gravitational waves that we should have seen. Many produce very small gravitational waves that we may never see. But in any case, gravitational waves did come and go in the past year and a half. They came on March 17th, 2014, to be exact, at a press conference at the Harvard Center for Astrophysics, where a group called BICEP2, that's an acronym for something that nobody remembers, but a group called BICEP2, you can look it up in the Wikipedia. The group called BICEP2 held a press conference and announced the detection of swirly patterns called B-modes in the polarization of the cosmic microwave background. And these measurements certainly are a tour de force. The fact that now they can not only measure the intensity of these very small fluctuations in the cosmic background radiation, but can also measure the polarization is really incredible. So they deduced that they saw these particular patterns which are indicative of gravitational waves in the early universe, which, if they were there, would be in agreement with inflation and would be a significant new piece of evidence in favor of inflation. And their original result, as they announced it, was that after accounting for the best estimate that they could make of the contamination due to dust, turns out that dust in our own galaxy can produce the same effect. They found what's called a tensor scalar ratio of R, of that value, with R equals 0, that is the absence of gravitational waves, disfavored at 5.9 sigma. All this sounds very technical, but the translation is that if this was right, this 5.9 sigma statement, if this was right, the probability that there are really no primordial gravitational waves is only about 1 in a billion. However, in spite of the fact that the probability by this analysis was only 1 in a billion, it seems to have turned out that way. Sometimes things that are estimated to have probabilities of 1 in a billion nonetheless happen. What happened is during the months and the year that followed this initial announcement, other groups looked at the estimates of the effect of dust in our own galaxy, and ultimately the conclusion was that there could be enough dust in our own galaxy to fully account for the signal. So there's no real reason to conclude from this data that we are seeing gravitational waves from the early universe. And the latest word really on this is a joint analysis by BICEP2 themselves and the Planck satellite folks. They pooled their data, and ultimately they concluded that we find strong evidence for dust and no statistically significant evidence for tensor modes. So that's the current status. But the search goes on. This is not really the end of the story. It's just the current status of the story. The search for B modes is still going on, and BICEP2 and other experiments are becoming more and more sensitive. So the level at which they could be seen is going down and down. If they are found, they would provide a fourth very important piece of evidence for inflation in my list of evidence. But even more than that, if they are found, they provide an important tool for studying the details of inflation. Right now, inflation looks very good, but we don't know much about the real details of what this repulsive gravity material was and how exactly it interacts and so on. So there's a lot to learn, and if we can find B modes in the polarization of the CMB, which would be knowledge about gravitational waves from the early universe, that would be a tremendous help. Currently, this quantity R, which characterizes the strength of the gravitational waves, is known to be less than 0.11. Tomorrow, there'll be an announcement of a better limit, 0.07. So progress is being made almost as we speak. And this will come out on the archive tomorrow. In the future, they think that by the middle of the next decade or so, that they can get down to R being 0.001, which is another factor of 100 of improvement compared to where we are now. So progress is really being made very rapidly. So the claim is that if R is bigger than this number, it will be found by about 2024 in a series of experiments that go by the general name CMB stage 4. And in particular, there's one of those experiments is what's called Lightbird, which is in fact an international collaboration centered right here in Japan. So very important work being done. If these B modes are not found, however, I do want to emphasize that that's not really evidence against inflation, because the intensity of this prediction depends very much on which inflationary model is right. And there are very plausible models of inflation that predict intensities for B modes that would be much, much smaller than 0.001 and would just not be seen. OK, now that finishes part 2 of my talk. I now want to move on to part 3, which is maybe the most fun. I want to talk about what inflation has to say about the possibility that we live not in a single universe, but instead in a multiverse, a system of many universes. So the key fact that drives this is that almost all detailed versions of inflation is really a collection of theories. It's not really a theory. And almost all detailed versions of it lead to a phenomenon called eternal inflation. And that leads to a multiverse. roughly speaking, eternal inflation happens because inflation is driven by a metastable state, a state that decays. And it decays like other unstable systems decay, like radioactive atoms. It has a half-life. You can't really predict where decay will take place, but you know that in a certain volume, in a certain amount of time, there's a probability of a half that it will decay. So if you imagine waiting for one half-life of the region you're looking at, you expect that half of the inflating material will become normal non-inflating material. But the thing is that the exponential expansion continues until the decay happens. So while you wait for half of the material to decay, the other half, because it's exponentially expanding, and in fact it's exponentially expanding faster than it's decaying, will at the end of this half-life be vastly larger than it was at the beginning. So even though you've waited and watched half of the region decay, the half that remains is now vastly larger than what you started with, and you've made no progress towards ending inflation. In fact, more and more inflation just keeps happening. And that means that once started, inflation seems, as far as these mathematical models go, to go on forever, with pieces of the inflating region breaking off and producing universes, which in this context we call pocket universes, just to indicate that it's not everything that exists. But these pocket universes would be like our universe. We would be living in one of them. We would be living in one of the infinity of pocket universes. Now, when I first started hearing people think about this, it wasn't really me who started it, but when I first started hearing people talk about it, I have to admit that I myself was not very interested in it, because I didn't think it had much to do with any real questions of physics. So what if there are other universes out there that we can't see? Why don't we just put those in science fiction books and go on doing science about the universe that we do see? But it turns out now that it actually is relevant to questions about issues that we do see. And I'll try to explain why. It goes back to this important discovery in 1998 that I mentioned earlier, that our universe is not slowing down under the influence of gravity, but rather our universe is actually accelerating. And according to general relativity, this requires some repulsive gravity material, similar in character to the material that drove inflation itself. And that's what we call the dark energy. And the simplest explanation, which is what I'm going to assume for the rest of this talk, is that the dark energy is just vacuum energy. Everything we've measured about it so far is consistent with it just being the energy of empty space. Now, an important feature here, which in fact was mentioned by Thomas, is that the modern picture of the vacuum is not emptiness. Einstein, I think, never would have considered his cosmological term to represent vacuum energy, because to Einstein, with classical physics in his mind, the vacuum was just emptiness. So to Einstein, it would have been hard to conceive that emptiness could have had energy. But the modern picture of the vacuum is much more complicated. We have electric and magnetic fields that are constantly fluctuating. We have particle-antiparticle pairs materializing out of the vacuum and disappearing. And now we've also confirmed that we have something called a Higgs field, which has a non-zero value throughout the vacuum. So the vacuum is a very complicated state, and there's no problem, therefore, recognizing the possibility that the vacuum could have a non-zero energy density. And that is the standard now interpretation of what the dark energy most likely is. People are still certainly exploring other possibilities as well. So the fact that it has vacuum energy is not so strange, but then you want to ask, can we understand the magnitude of this vacuum energy that we're observing? Does it make sense according to our theories? And the answer is no, it makes no sense. It's a colossal discrepancy between what we would expect. I should first say that we don't know how to calculate the vacuum energy density. So this is not really the failure of a calculation, but rather the failure of an estimate. but we can estimate it. And the natural estimate is what's called the Planck Scale, which is basically the energy scale at which the effects of quantum gravity are expected to become important. And this Planck scale is much larger than the observed value of the vacuum energy. In fact, it's larger by a full 120 orders of magnitude, making it certainly one of the most colossal failures in the history of theoretical physics. So how do we understand, how can we hope to understand why the vacuum energy in our universe is so vastly smaller than what theoretical physicists would expect? Well, of course, one possibility is that they're all idiots, but we'll dispense with that possibility and try to look for something more consistent with the idea that theoretical physicists might know what's going on. So first item here is just a reminder that one of the thorniest problems in particle theory today is to understand why the energy density of the vacuum, which is the same as the cosmological constant, is 120 orders of magnitude smaller than the expected scale. The multiverse offers a possible explanation. It's certainly controversial. I don't want to advocate that most physicists believe that this is the right explanation. Many do, but there's no consensus. But the multiverse certainly offers a possible solution. And that's related to the fact that according to string theory, there's not just one kind of vacuum. But according to string theory, there are perhaps something like 10 to the 500 different kinds of vacuum. And each of these pocket universes, as it forms, will randomly choose one of these different vacua to fill itself with. So the different pocket universes will all be different, and each will have their own vacuum energy density. And they will span the range going from plus the Planck scale to minus the Planck scale. Negative values are allowed. So we just have a tremendous expanse of possible values for the vacuum energy. That would then certainly allow many, a huge number, in fact, of different types of vacuum that would have energies as low as what we observe, just because you have so many to choose from. But then there's the question of why should we be living in such an unusual vacuum? It would still be unusual in the full spectrum of possible values. And there's a possible answer, which is that the vacuum energy is not just a number that sits on the side. It really affects the evolution of each pocket universe. It determines the acceleration of the pocket universe. So if it's too large and positive, the universe would just fly apart so fast that you would not expect life to form. Conversely, if the vacuum energy were negative and somewhat larger than what we observe, the universe would rapidly implode. And then again, you would expect life not to form. So it is quite believable that life only forms in that narrow range of pocket universes where the vacuum energy happens to be incredibly small, something like 120 orders of magnitude smaller than a typical value. And that's the theory, sometimes called the Anthropic Principle. It's sometimes just called observational selection. The idea is that life would only form in universes with incredibly small vacuum energies. And then even if in the multiverse, most places would have huge vacuum energies compared to what we observe, most living things would see very, very small vacuum energies like what we see. And most of us regard that as an explanation, if it's true. I'm going to close just by giving you a sampling of how different physicists react to this idea of a multiverse, because, as I said, it is somewhat controversial. So I want to quote three, actually, beginning with Sir Martin Rees, who is Astronomer Royal of Great Britain and former president of the Royal Society. He's also former Master of Trinity, and he's been knighted. He has almost every honor you could imagine, short of the Nobel Prize. And he was at a meeting, which I think is actually held at his residence, asking people how certain they were of the multiverse. And he said that he is sufficiently confident about the multiverse to bet his dog's life on it. He does, by the way, write about the multiverse, and he is a proponent of the multiverse. So that's interesting. He presumably likes his dog a lot. I've never met his dog, so I don't know for sure how cute the dog is. But that's a pretty strong statement. Now, at that same meeting, I was not at the meeting, by the way, but at that same meeting was Andre Linde, who's now at Stanford, who played a major role in developing inflationary cosmology, and one of the people with whom I shared the 2014 Kavli Prize for the development of inflation. He was at the meeting, and he's a big proponent of the multiverse. So he immediately chimed in and said that he's so confident that he would bet his own life on it. So that's extreme confidence. And he's a Kavli Prize winner, so we have to take that very seriously. Now, a third person I want to quote is Steve Weinberg, who's the inventor, really, of the electroweak theory of particle interactions, for which he won the Nobel Prize in 1979, and a very prominent physicist, and from my point of view, a very strong voice of reason. I first knew him as a graduate student. He was on the MIT faculty when I was a graduate student at MIT. I developed an enormous respect for him, which I still have. He said, he, by the way, was not at the meeting, but commented later, seeing these other comments quoted in the press. He said that I have just enough confidence in the multiverse to bet, think of something clever. He said he has just enough confidence to bet the lives of both Andre Linde and Martin Rees's dog. And I'll stop there. Thank you.
Guth 博士、ありがとうございました。
Well, thank you so much, Dr. Guth, and let's take a few questions from the floor. Please raise your hand if you have any question. Please wait for my recognition. And keep on raising your hand until you receive the microphone. Please, a person at the third row. Well, thank you for the wonderful presentation today. From the CERN, there is an accelerator experiment going on, and some values have been measured at the CERN. And the supersymmetry or multiverse theory, which is correct, the measurement taken by CERN can be one of the evidences to see which one of the two theories are correct. So how do you react to the findings of the CERN's accelerator used experiment?
No?
Yeah, I'm sorry, I didn't.
So the question was about the energy density of the Higgs.
Sorry?
And the question was about the energy density of the Higgs contributing the vacuum energy overall. And so according to the Higgs boson that have been discovered, there has been the discussions whether that is actually supposed to account for the multiverse or not. So where are you on this question?
Okay. Let's see. First of all, the vacuum energy of the Higgs itself, as a contribution to this Planck scale that I'm talking about, is negligible. The Planck scale is the scale at which we think quantum gravity will become important, and it's much higher than any scale reached by accelerators, while the scale of the Higgs field we have now reached. But the Higgs does raise questions about the multiverse, because theoretically, it's hard to explain why the mass of the Higgs is small compared to this Planck scale, which we know it is small compared to the Planck scale. Theoretically, one has to fine-tune the underlying parameters of the theory to extraordinary degrees to make the Higgs mass turn out to be as light as what we observe. One possible solution to this Higgs mass problem, called the hierarchy problem, by the way, one possible solution to this hierarchy problem is called supersymmetry. It's a symmetry which says that besides the particles that we see, every particle that we see has a partner which has the opposite Fermi-Bose quality. So for every fermion, there should be a partner boson someplace that we haven't seen yet. And for every boson, there should be a partner fermion someplace that we have not seen yet. The supersymmetry has the nice feature of canceling out the terms in the calculation which caused the Higgs mass to become so large. So if supersymmetry were found, that would explain why the Higgs mass was so light, or at least could explain it. And people have looked for supersymmetry for that reason. But supersymmetry has not yet been seen at the LHC, even though it's been looked for. It's certainly not been definitively ruled out, but it's looking less and less good as the region in which it can be found has gotten smaller and smaller. If supersymmetry is not found, and nothing else that we might not foresee, and nothing else is found that might otherwise explain why the Higgs mass is so light, then in fact the Higgs mass will become a further piece of evidence for the multiverse. It's not clear how many people will be convinced on the basis of that, because the multiverse, the evidence is certainly indirect. But if supersymmetry is not found, the fact that the Higgs mass is so light becomes very hard to explain and certainly points towards the possibility of a multiverse.
はい、じゃあ他に質問ありますか？じゃあその後ろの方。
Anything else? The person at the back. The person at the third row or fourth row from the back. Well, thank you for the wonderful presentation. I'm just a lay citizen, so I have a very basic question for you. First question, you have said that one energy is negative. So one of the energy is negative. That is why energy density can be constant. And when under the expansion, you said that the law of conservation of energy will hold. But some of the astronomers will say that there is an interstellar material which releases the energy, and it becomes a star and starts to emit the light eventually. So if the energy is minus, then if the interstellar material is solidified, then star will be cooled so that it might not be able to release light. So how do you explain that? About the repulsion. So first question, would you like to answer? Did you get it?
I think so. The question, as I understood it, asked me whether or not this cancellation between positive energy of matter and negative energy of gravity would work if the matter starts doing complicated things like forming stars and so on. And I think the answer is that conservation of energy is a principle which is essentially golden as far as physicists know. As far as we know, all the laws of physics impose conservation of energy. So as long as conservation of energy works during the inflationary process itself, which it does, and there it is just a simple cancellation between two forms of energy, the positive energy in the form of this repulsive gravity material and negative energy in the form of the gravitational field. As long as energy is conserved through that process, which it really has to be if it's described right, then whatever happens after will also conserve energy, and the energy will continue to be whatever it started out to be, and that could be zero for all that we know.
じゃあその2つ目の質問を。
So please go to the second question. I have a second question. So prior to and after inflation, the repulsion power is the same? And you have mentioned that the dark energy is still expanding, but when it comes to inflation, very starting time of inflation, what is the strength of repulsion before and after the inflation? And also, under the multiverse, do you think the same old physics law would hold or not?
Questions there from what I heard. One was how does the strength of gravitational repulsion compare between inflation and the gentle acceleration that we see today, the fact that today we see the universe accelerate? And the answer is certainly that they're vastly different. One can talk about the doubling time. The doubling time during inflation was something like 10 to the minus 38 seconds, perhaps. We're very uncertain about that number because it depends on the energy scale of inflation, which we don't really know. But a typical number for early universe inflation would be 10 to the minus 38 seconds for the doubling time, while the doubling time of the current acceleration of the universe is more like 10 billion years, which is a lot longer than 10 to the minus 38 seconds. So the acceleration today is vastly slower than the acceleration that we're proposing for the early universe. Then I think separately you asked, would the laws of physics be different in the different pocket universes of the multiverse, which is also a very important question. The answer that we are theorizing is that the ultimate laws of physics should be the same everywhere. We really don't have enough imagination to think about anything else. So if the laws of physics were different any other place, we just have no way of knowing about those places, so we don't try to talk about them, like heaven or whatever. So the ultimate laws of physics we think of as being the same, but if the ultimate laws of physics are as complicated as string theory, even if it's not string theory, if they're as complicated as string theory, then there's more than one kind of vacuum, more than one kind of a stable state that you could be living in that could look like the vacuum around you. And each type of vacuum would carry with it its own behavior, even though the ultimate laws of physics would be the same. So maybe an analogy would be that even though the laws of physics are the same, we might imagine ourselves living in air or living in water or living in liquid nitrogen. And the world around us would look very different in those cases, even though the laws of physics would be the same. And that's the situation with the multiverse. So there are perhaps 10 to the 500 different kinds of vacuum, and each of which would seem very different to the people living in them, if anybody did live in them. But the ultimate laws of physics would be the same.
エブさんさんが質問があるようなので、そちらのマイクお願い。
So Professor Ebson has a question. So it's a battle between the laureates of Kavli Prize.
I have just a very simple question. Do I understand correctly that to keep this energy balance to zero, as the universe expands, new matter is created?
Yes. During inflation, as the universe expands, the density of matter remains constant. And that means new matter is being created,
and
yes.
So in this present phase, is matter created right now? And if so, do we see the creation of matter? Can we see it by experiments?
Okay, you're talking about the present phase of accelerated expansion. The answer is yes, matter is being created, we think.
Yeah.
If you ask, do we see it? Not exactly. The new matter that's created is just the new dark energy that fills the ever-enlarging region.
Oh, okay.
So if the dark energy is really there, it's increasing in its volume, and therefore it's increasing in its amount.
There's no dark,
but we don't directly observe the dark energy.
No matter.
Sorry?
There's no matter per se.
There's no ordinary matter, that's
No.
right. The extra, the new stuff that's being created as the universe undergoes the exponential expansion caused by the dark energy is just more dark energy.
Okay, thank you.
じゃあ真ん中の島の4列目、女性の方。
The lady who is seated at the fourth row from the front. Well, Mr. Guth, I knew you by photo, so it's a great privilege for me to see you in person today. Thank you very much for your wonderful lecture today. Well, Lightbird, led by Mr. Hadley. Maybe the inflation theory will hold even no discovery is made by the Lightbird, because there are some other studies going on. Sorry, I'm a total layman, but I have no imagination. But what is other parallel researches which are underway apart from the Lightbird, which is a Japan-centered research or workshop?
Okay. The question is what research projects are underway to continue the tests of inflation other than Lightbird? And the answer, I guess, is that there's a lot of them. Certainly on a shorter time scale than Lightbird. The BICEP2 team is continuing their studies, and they now have a new detector called the Cac Array, and they're continuing to use both the Cac Array and the original BICEP2, which actually has now been upgraded to what they now call BICEP3. There's also something called the South Pole Telescope. There's also an experiment called SPIDER, which was a balloon-based experiment, was and is. They have data currently from a flight of their balloon that they have not yet released, and I think they are also intending further flights. So there are really a great many experiments underway. And there are also other types of experiments, like, for example, experiments that aim at looking at the hydrogen recombination line throughout the universe, which can provide more three-dimensional data of what the sky looks like. The CMB is really only two-dimensional. Research is actually happening very quickly. And as I mentioned, there's a new result to be announced even tomorrow on a limit for the value of little r, the strength of gravitational waves in the early universe. We've been living through very exciting times, and they will continue to be very exciting.
Alan, I think the question was a different one. So
sorry.
suppose the light bird would not see the signal all the way down to the 0.001 in the Tensor
okay.
scalar ratio.
Was that the question?
What would it mean for inflation? What kind of inflation is still
I'm sorry, I
viable?
misunderstood the question then. Sorry. I'll try again. One thorny issue really concerning these tests of gravity waves is that we really don't know what the prediction is. Inflation right now is still a whole class of models which make a broad range of predictions for the gravitational wave intensity. So if it's not seen at the level of light bird, at the level of 0.001, there are still many inflationary models that would be perfectly viable, that would be consistent with that. From what I understand, the experimentalists think that ultimately we might be able to get to 0.0001, another factor of 10. And beyond that, I don't think anybody even has any ideas about how to do it, because it becomes very, very hard to subtract out backgrounds and things. So it's not clear we'll ever know more than down to the level of 0.0001. And it would be great if we see gravitational waves in that range, but it's also okay for inflation if we don't.
And so what kind of inflation is that? Suppose we don't see the signal? What's the difference?
It's inflation that happens at very low energies, where the potential energy function for this field that drives inflation has a hill where even the top of the hill is at a relatively low energy.
よろしいでしょうか。他に質問、じゃあ一番後ろの方。走るの大変ですね。
The person at the back, please. So person is running to hand over the microphone. So thank you very much for the valuable presentation. I have a simple question. So is the universe transitory, or is it repeatable, recurring, cyclic cosmos or universe? Which one is that? Ours is a part of a universe cycle instead of a standalone single one-off universe, which is correct. You have mentioned about the endless inflation. So if that is the case, then just the other day I heard from Professor Murayama's presentation, there is a theory about big rip, the end of a universe, that the universe will get ripped and get disappeared in the end. If that is the case, then something like a big crunch could happen as well. Then cyclic universe theory will hold. Any thought on this? Anything?
Question. And the question involves certainly many things that we're very uncertain about. So there is no definitive answer, I don't think, to the questions you're raising. But you're asking about what is the ultimate scheme of the multiverse. The simplest version of eternal inflation that I spoke about would lead not to genuinely cyclic universes, but to an infinite succession of universes. So in standard eternal inflation, one would have an inflating backbone of space growing exponentially, and at random locations in space and time, big bangs would occur and local pocket universes would form. And the pocket universes would go on forming forever, so time will never end. There will always be living beings enjoying themselves throughout all of time to the future of now. But it's not actually cyclic in the sense of a universe getting big, getting smaller, and getting big again. Now, there are other theorists who talk about exactly that theory, the theory that there's essentially one universe that gets big, gets small, and gets big again. I guess both Steinhardt and Turok together have a model like that, and Penrose has a different model like that. And those certainly are outside possibilities. From my point of view, they're much, much less motivated than inflation. But you might say I'm biased. I probably am. And then, let's see, you also asked about big rips. The big rip is certainly a possibility. There certainly are kinds of physics that would cause regions of space-time to essentially disintegrate. And similarly, there's kinds of physics that would cause regions of space-time to collapse to singularities. And I have to admit that I would say that we're very uncertain about what the aftermath would be for either of those scenarios. We don't really understand how to think about space-time quantum mechanically. So these descriptions of big rips or collapse to a singularity are all really based in the language of classical general relativity. And classical general relativity allows these singularities, allows space to just end. On the other hand, quantum theory, as we know it, doesn't actually allow anything to end. Quantum theory is built in at the very ground level is what's called unitary evolution, which really means that things just continue and continue, and everything is reversible. At any time, if you know what the state is, you can, in principle, calculate backwards and find what the state was earlier. So that's inconsistent with the idea of space disappearing at these singularities. And since we don't have a viable amalgamation, a valuable union between classical general relativity and quantum theory, I think we really don't know how things are going to play out, whether these singularities really mean the end of space or whether something happens to allow space to resume.
あと一つぐらいですね、質問。
Maybe one more question we can entertain from the floor. Please.
I could ask you this privately, but there might be general interest in the question. And the question is, the universe is now accelerating in its expansion. So imagine that we are 1 billion or 2 billion or how many. The sun has not yet died out, and we're still around somehow, far enough in the future. If you looked up in the sky, having the expansion we see, things will have disappeared. You may look up and see essentially a black sky. If we got to that point in time and you were around, what would you be thinking about the universe you would then observe? Because it would seem to you, at that point, empty or close to empty. So how do you reconcile the observer? Right? You talked about an Anthropic Principle. So if I'm out there and I'm looking at the sky and I see very little and I'm trying to derive laws of physics, what laws of physics would I derive?
Okay, so certainly an interesting question. If we were living 50 billion years in the future or something like that, the sky would look very empty if the acceleration that we're seeing now persists as we expect it to. Then that would not contradict anything that we now think. That is, this is all part of the theory that we're now proposing. So the theory that we're now proposing would still be quite viable, but it would also be harder to develop it because there'd be much less evidence. You'd hardly be able to see anything. The cosmic background radiation also gets weaker as the universe expands. So measurements of the cosmic background radiation would become harder and harder. And it's a little hard to say what physics might be like then, or even if life can exist then. So I don't know. I think I wouldn't really know how to speculate. Certainly true that physics would become a lot harder, or at least cosmology would become a lot harder if we were living 50 billion years from now. But still probably not impossible. There would be traces. And given how amazing people have gotten to be in their abilities to detect very low levels of cosmic background radiation, it might still be possible to see the CMB and ultimately get graphs like the one I showed. But it would take a higher level of technology. But in 50 billion years, who knows? People might have that technology.
Are you happy? He doesn't look happy. まあ、残念ですけども、時間になりましたので、これも改めて。
Although it's unfortunate time has come, thank you very much. Thank you, Professor Guth. It has been 3 hours and a little more with Kavli Foundation and Norwegian Academy. Professor Ebbesen and Professor Guth gave lecture on basic science. It was a good opportunity to raise awareness of basic science achievements, and we are thankful that the laureates came to Japan to give lectures. This is a biennial prize. Prize is awarded biennially, and 2 years from now, we may be able to hold another lecture session in Japan. Organizing such an event is not easy. Since the end of last year, we have been planning and preparing, and many people were involved in the arrangement for this event. And over a long time, in the planning, those who were involved, I would like to ask them to stand up and be acknowledged. Snifted Emsted from Norwegian Embassy, Suvain Gladom, and Yoko Nakatsukasa, and from Kavli Foundation, Nadine Stan, and from IPMA, Yuko Enomoto, who may be working somewhere. So this is not easy, but we are very grateful that we are finally able to have had that lecture session today. Sadly, the event comes to an end. Thank you very much.